Welcome to Sigma Solver, guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. Today we are going to talk about a new topic, which is graphlets. So let's read the question first. What are graphlets? With reference to 3 node graphlets, find the graph degree vector GDV for node V. So here is the figure and we need to find the GDV of node V as well. So first we look into the concept of graphlets. So the real world application of graphlets can be understood in social networks. They help in understanding the small structural patterns. So like in a group of friends or in a network of multiple friends, how they are connected in multiple small groups, that is an instance of a graphlet. Similarly, in biology, they can reveal essential motifs in protein interactions, which helps in the discovery of new drug targets. So whenever there is a concept of clustering and small graph properties, we kind of refer back to the concept of graphlets to understand them in a structured way. If we want to understand this in a more formal way, then we can say that graphlets are basically small, rooted and connected non-isomorphic subgraphs. There are a lot of technical terms here, but let's understand them one by one. So first is the word rooted. So rooted means that a specific node in a subgraph is treated as a point of reference. So a subgraph kind of gets us a feeling of a tree, and if it has a reference point which can be considered as the root node, then we say that the graph is rooted. Next, connected. So if in a subgraph all nodes are basically reachable from the parent node, which we considered here, then we say that the graph is connected. Next is non-isomorphic. Non-isomorphic states that each graphlet is structurally unique. No two graphlets are identical after rearrangement of nodes and edges. So it's similar to structural isomorphism, and no matter how you interchange the nodes and edges, two non-isomorphic graphlets cannot become same. So if you want to understand the concept of graph isomorphism in a bit more detail, then I have put a link in the top right corner up here for your reference. So please check it out. Matter of fact that if you want to check two graphlets and see whether they are basically isomorphic or not, so there does not exist a polynomial time algorithm to do that. Not only that, we are not yet able to figure out a method to basically reduce it into another NP problem. Therefore, it is also not NP complete. This checking or evaluation of two graphlets to be isomorphic or not is therefore an NP hard problem. Now the next part is the identification of graphlets. So here we will understand the different graphlets starting from node 1, 2 and so on. So node 1 is obviously only one graphlet and it's quite trivial, so it is not considered during calculations, but we will consider two node graphlets. So in two node graphlet, you can see that I have put 0 mark for this particular node, right? So this graph G0 has 0 at one end. So the argument can be that this also will be 0. And it's understood that it is also 0, right? Because the perspective when you demarcate this node as 0 will be same if I twist the graph and then tell that this is 0, right? So it's just about perspective. Similarly, if we see 3 node graphlets, then for G1, which is a separate graphlet from G0, we will say that 1 is a separate node and then 2 is a separate node, but then this node will again be 1, right? It cannot be pointed as 3. Why? Because the perspective of this particular node in this graphlet is same as 1 here, right? That's why we will say that both of them are basically 1, and therefore I have marked nothing towards this. Similarly, if you see for G2, this node will be marked as the third node in this line that we are following. So you can see a pattern of numbering starting from 2 node graphlet, continuing in 3 node graphlet, and therefore continuing again on 4 node graphlets as well. So here you see that 3 is identical in these places. So all these are 3 only, right? So up till now we have 4 positions that will exist in any graph containing at least 3 nodes. Not all may exist, but at least one of them has to exist. Now 4 node graphlets. So in 4 node graphlets, again the same thing, 4 will be here and then 5 will be here. Similarly 5 is here and then again 4. In here you will find 6 and 7, then 8 for G5, then 9, 10, 11, then 12 and 13, and finally 14. So if we look into this, we found that we got 6 graphs that are different in shape that can be created from 4 node graphlets. Similarly, we had got 2, in this case 2 graphs, and here just 1. But in our question we were asked to only give the Graphlet degree vector with respect to 3 node graphlets. Means we need to consider up till 0, 1, 2 and 3. But it's beneficial to understand that you get 13 different positions up till 4 node graphlets, which counts total up to 14. Next, there can be 4 node graphlets, as I just told you. Next we come to Graphlet degree vector. So a Graphlet degree vector is basically a count vector of the number of graphlets rooted at a given node. So in our case it will be V. So if we go in the particular instance, we need to understand how many graphlets are basically rooted at this particular node V, which is under consideration. So the list of graphlets that we will be dealing with is this one, as we just calculated above: A, B, C and D. You can see A, B, C and D, right? So the naming is the same, it's just the nomenclature that has been changed here. So instances of A, B, C, D, if we just see, A can be represented as the top edge in the triangle or the lower edge in the triangle, but its perspective remains the same. Then B can be represented as this in the triangle. Remember that we are not considering the attachment at this point, neither at this point, right? We are only concerned with the detached subgraph that resembles the perspective B has in this graphlet. Similarly, we have this particular A and its counterpart below. But if we see for C, letter C, then there exists no such graphlet where either of them are the terminal or ending edges. Why? Because if we come here, this node which falls between 2 nodes, one of them is a terminal, this one, but this is not a terminal. Again, this is not a terminal, but this is a terminal. So we see that there is no C element in the graph where the root node is V. So for D, if we check, that is the terminal edge when there exists a 2 node chain after it. So then we can say that D is this particular node which is V, and then we have the rest of it. Similarly, D can be again put here and then the rest of it. But in either of these are different because of the structure of the given problem. Therefore, what we can say that the GDV of node V is A2, B1, C0 and D2. Why A2? Because A has 2 structurally different representation when V equals A. Similarly, B has only one instance where V equals B, but again V equals D has 2 instances. Therefore, this is the Graphlet degree vector for node V. So that's how you calculate Graphlet degree vector for a given node, and this calculation is basically based on up to 3 node graphlets. There can be more number of graphlets as well, that is 4 node graphlets, 5 node graphlets and so on. Calculating graphlets is again an NP hard problem, so yeah, it's a challenging problem to deal with, and kind of increases exponentially as the number increases. So for 5 it goes up to 72 around. Yeah, so that's been it. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.